Hi. So for this part 2, right, of the enzyme chapter, I will focus on the characteristics of enzymes, okay, including temperature and pH. So let's begin by talking about some of the characteristics of enzymes. So number one, right, enzymes can catabolize and anabolize. The word is probably not very familiar to you, but so you can wait. Okay, sorry. Yeah. So you can think of catabolize, right, as breaking down, which is actually what I mentioned in the first video, and anabolize, right, as synthesize. Okay. So enzymes, right, can break down substrate molecules into smaller molecules, or enzymes can take smaller molecules and build them to make a bigger molecule. Okay, so enzymes can work both ways. All right, so these are some examples of enzymes in this aspect. So the formation of polypeptides and proteins by ribosomes. Ribosomes makes proteins, right? So they are able to do this. Okay, formation of glucose in photosynthesis is an example of anabolize because I can take small molecules and I can make them. And digestion, right, is of course breaking down. Okay. Number two, enzymes, right, are very specific in their actions. As you can see in my first video that I talk about complementary active site of an enzyme. So they don't work on anything. They must work on a substrate that is very specific. So substrates that are complementary to the active site of the enzymes are able to form enzyme substrate complex, and so the reaction will work. Okay, and this is known as the lock and key hypothesis. So in the lock and key hypothesis, right, enzymes are likened to be the locks, substrates are likened to be the keys. Okay, with a unique key, I can unlock a lock. I cannot take another key, right, and then push it into a normal lock because it doesn't work. So the correct key must fit the correct lock. And so this example, right, is known as the lock and key hypothesis. And this actually shows, right, enzyme specificity. Okay, enzymes are specific in their actions. Enzymes can speed up chemical reaction, and that is a characteristic of enzymes. They are able to do that because they lower activation energy, which is actually being mentioned in the first few slides of part 1. Okay, so this is a characteristic of enzymes. Enzymes, right, are not needed in large amounts. Actually, right, you don't need a lot of them. You just need a little bit of, lesser in quantity of them to carry out a reaction because they are not destroyed after a reaction. This is also found in your definition of enzymes. So enzymes are chemically unchanged after a reaction. Okay, and so the enzymes can be reused over and over and over again. Enzymes are actually found everywhere around you. Okay, this example that you are looking at right now is a very common example. There are enzymes, right? They are found in washing powders. And so if the enzymes are not destroyed after a reaction, right, the enzymes can be reused over and over again. And so when you use washing powder, right, you realize that you only need to put a scoop in a huge load, and this scoop is enough to clean the clothes. Correct? It's enough to break down stains, break down blood stains and food stains and whatever. And so it's because, right, the enzymes in the washing powder are not destroyed and they can be used over and over and over again. Okay? Now, the last two characteristics of enzymes are a little bit more elaborated. So I'm going to focus on the first one. Enzymes are affected by temperature. Okay? Um, and you are looking at the temperature graph over here. This is considered low temperature. This is considered low, and this is considered high temperature. Okay? So you can see, right, that the rate of reaction, right, at different temperature of an enzyme is different. Okay? So let me start by going through the words. At low temperature, right? At low temperature over here, okay, enzymes are considered inactive. That means, right, they are very slow in their reaction, okay, and so the reaction, right, even though it happens at this temperature, it is a very low reaction because the enzymes are inactive. Okay, we describe the activity as being inactive. If I slowly increase my temperature, right? If I slowly increase my temperature from very low to maybe, yeah, I just add on the temperature, the enzymes, right, will start to work harder. And so the rate of chemical reaction, right, actually increases. You can see in this graph, right, that is actually going higher and higher and higher. Okay, now why is that so? If you remember the particulate nature of matter, as temperature increase, right, all molecules will move faster. Okay, they will vibrate and they will move faster. And so in a solution, right, the kinetic energy of all the molecules, okay, the enzymes and the substrate molecules will increase. So this increase in movement of enzyme and substrate molecules, right, will cause them to bang into each other more. Okay, so I use the word bang over here because I'm explaining, and you can see in the slides, right, that it creates, right, this increase in movement creates higher collision rate. So the enzymes and the substrate molecules, because they are moving randomly faster, there is a chance, right, that they will collide more. And when they collide more, right, there will be a chance that the somehow, right, the active site of the enzyme, right, can just nice fit into the active site, just nice fit into the substrate molecule. Okay, because they are moving more, they are colliding into each other more, and so there is a chance that they can form more enzyme substrate complex. And if they can form more enzyme substrate complex, it means that the reaction will start, and so more products will form. So increase in temperature makes the reaction faster because of this theory, okay, which I'm highlighting here. And this theory is important, okay. Yeah, important means you must study lah. All right. So the reaction, right, will continue and continue. So it will go higher and higher and higher, right, until a very specific temperature. We call this temperature the optimum temperature. Okay, this is the peak, and this temperature, right, is the temperature in which the enzymes, right, is performing at its best. So we call this temperature the optimum temperature. And over here, right, if you take a look at the rate of reaction, it is the highest really. It cannot go any higher really. Okay, so we call this temperature, right, that creates the highest rate of reaction, optimum temperature. However, right, if we continue to push the temperature forward, the enzymes, right, okay, so over here you can see the highest rate of chemical reactions over here, the explanation. And what I'm trying to say is, okay, sorry, here, okay, as the temperature increase further, right, from the optimum temperature, the enzymes, right, will start to denature, which I will explain further in the next slide. Okay, so this denaturation of the enzymes, right, will slow the reaction down, because when the enzyme denature, right, the active site of the enzyme is permanently changed, is altered. And when it is altered, right, it is unable to bind to the substrate because they are no longer complementary. And if they cannot bind to the substrate, they cannot form enzyme substrate complex. And so, of course, the reaction will not work. Okay, the reaction will drop until it becomes zero. So this is where the enzymes will start to, inverted commas, start to die. Okay, but you cannot write die. The correct word is known as denaturation. Okay, so this is an example of a denatured molecule. When a molecule, this is a normal molecule, okay? So this molecule is folded in a very nice way. So when the molecule is undergoing heat denaturation, right? In this case, denaturation can be by heat, can be by other things. This molecule, right, will change the shape. So it becomes no longer the same as before. And so, right, if I have a substrate here, the substrate, right, will not be able to bind at it because the shape has already changed. So we call this denaturation, and it is caused by heat or chemicals, okay, such as acid and alkali. So after we talk about temperature, right, let's move on to the last characteristic of enzymes, which is pH. pH is also a factor that determines enzyme reaction. Okay, so you're looking at a pH graph over here. Of course, the pH is here. Okay, now all enzymes, right, have an optimum pH. That means for every enzyme, right, have a unique pH, right, that it can work best. So example, right, some enzymes in the stomach thrives in acidic pH. Some enzymes in the small intestine, right, thrives in alkaline pH. If I were to take these enzymes and I were to put them switch them around, right, they will not work because the pH it's not suitable for them. Okay? If the enzyme, right, is exposed to a pH that is too far from the optimum, okay, the enzyme will undergo denaturation. So over here, right, example, if this particular enzyme has an optimum pH of X, right, if I were to increase the pH over here, it will denature. You can see that the graph drops. If I were to shift it in the other way around, right, you can see the reaction drops also because over here also denature. So for pH, right, both ends, right, is actually denaturation. For temperature, at low temperature, it is not denatured, it is inactive. At high temperature, then it becomes denatured. All right, so you need to remember this, and you cannot be confused for temperature and for pH. Okay, this is also my last slide, and this is also the last part for the chapter on enzymes. Okay, which is chapter 4. All right, so at the start of video 1, right, I talk about the definition of an enzyme. I talk about how enzymes work. For this particular video, I focus on the characteristics of enzyme, which is quite a lot. And the most complicated example to describe, right, and explain is the factors of temperature and pH on enzymes. Okay, so please go and read through your notes, and if you have any questions, please consult your teachers. And I hope this set of video helps. All right, thank you. Bye.